1 second in late autumn, 11 o'clock at night, a basement light hums cold and fluorescent. 8 seconds in, a hairline crack stretches along the slab. 3 feet, maybe 4, slightly wider than last winter. 16 seconds in, $8 of liquid on a hardware store shelf can close that crack from the inside. Not just patch it, close it. 25 seconds, it grows new stone where the gap was. The chemistry was first documented in 1825 and has quietly been used by industrial flooring contractors for over a century. 40 seconds in, the title says, "Big Concrete does not want you to know this," framing sharper than truth. And what truth replaces is stranger. 49 seconds, there is no big concrete cabal. Instead, a quiet economic structure erases effective solutions when they do not fit a profitable model. The Romans had one version of this chemistry. A wall in Provanum, Italy, still holds it together after 22 centuries. The Massachusetts Institute of Technology proved how it works in 2023. Today, it sits on a hardware store shelf for the price of a sandwich. The reaction that never finished. Concrete is not a rock. It is a chemical reaction paused in suspended animation when Portland cement meets water. Microscopic crystals of calcium silicate hydrate, or CSH in cement shorthand, grow and lock sand and gravel into a solid mass, a principle established by Trevor Powers in the 1940s. This reaction can fully complete only when the water-to-cement ratio is above 0.42. Below that ratio, some cement particles remain dormant, chemically alive, but isolated from the water they need. Nanoindentation studies by Van Dam and colleagues measured the unhydrated cement content in dense pastes at around 30%, meaning roughly a third of the original cement, even years after pouring, remains chemically idle. A 2023 review of rehydration studies published in the journal Materials found that in concrete with a water-to-binder ratio of about 17 to 22% of the cement remained unreacted. These dormant grains can rehydrate when conditions are right. Surrounding them is another substance with a quieter story, calcium hydroxide, mineral name portlandite, common name free lime, which forms naturally during the original hydration. Hardened cement paste is roughly 15 to 25% calcium hydroxide by volume. Pennsylvania State engineering literature places it at 20 to 25% for normal mixes. Free lime adds almost nothing to strength. It dissolves in water, creating microscopic capillaries that allow water to seep in, freeze, expand, and split the slab. Every cracked driveway, every dusting basement, every weeping foundation wall tells the molecular story of calcium hydroxide doing what calcium hydroxide does. The chemistry to turn that liability into an asset existed before the United States entered the First World War. In January 2023, Admiral Masick, professor of civil and environmental engineering at MIT, published a paper in Science Advances, examining a wall in the ancient Italian town of Privernum, conquered by Rome in the 4th century BCE. The wall is still standing, the concrete remains bonded. Masick and his team had been puzzled for years by small white chunks embedded throughout Roman concrete, called limeclasts, which earlier scholars dismissed as sloppy mixing. The team's microscopic and X-ray analysis told a different story. These clasts were not mistakes, they were reactive reserves. When microcracks form in Roman concrete and water reaches a limeclast, the lime dissolves, releasing calcium ions into the water. The calcium-saturated solution flows back into the crack and recrystallizes, sealing it from the inside. Massachusetts' team reproduced this effect in the laboratory. Hot-mixed Roman-style concrete healed cracks up to 0.6 of a millimeter wide. Modern Portland concrete generally cannot heal cracks beyond 0.3 of a millimeter. In 2024, Masick returned to Pompeii to a house frozen mid-renovation when Vesuvius erupted in 79 CE. Standing in the half-finished room, he later told Scientific American that he felt like a worker from that exact year. The Romans were not running a research program. They were running a recipe. The recipe carried its own ingredients, the means of self-repair. Roman permanence was not about building something that could not break. It was about building something that could repair itself. Modern engineering, almost without realizing it, chose the opposite philosophy: design for replacement. About 15 miles east of Pompeii, roughly 14 centuries later, masons of the Ming Dynasty built city walls and long mountain stretches of the Great Wall using a mortar that should not have worked. They cooked sticky rice into a porridge and mixed it with slaked lime. The result has held bricks together since. Around the year 1500, Bingjin Zhang, a chemist at Zhejiang University, led the team that figured out why. Using chemical analysis and scanning electron microscopy, Zhang's group showed that amylopectin, a branched starch molecule abundant in glutinous rice, acts as a growth inhibitor on calcium carbonate crystals. The mortar develops a denser, finer-grained microstructure than pure lime. It resists water and absorbs earthquake shocks. A Ming tomb sealed with this mortar reportedly survived a direct hit from a modern bulldozer. 2 civilizations, 2 recipes, the same underlying principle. a binder that does not merely set, but contains within itself the means to fill inevitable cracks. This principle predates modern patents and belongs to no one. In 1825, the German chemist Johann Nepomuk von Fuchs documented a procedure for producing what he called water glass, a clear, viscous solution of sodium silicate made by fusing sodium carbonate with silica sand. The compound was not new in nature, but Fuchs gave it a reliable production method. From that moment, the silica chemistry the Romans had drawn from volcanic ash became something a chemist could pour from a beaker. For most of the 19th century, water glass was used for fireproofing, preserving eggs, and as an adhesive. The bridge to concrete chemistry came in the early 20th century. Rudolph J. Wigg, an associate engineer at the United States Bureau of Standards from 1910 onward, published a long series of papers on Portland cement mortars and concretes. His work with co-author P. H. Bates on absorption and permeability, and later studies on alkali water and seawater effects, were the first systematic American documentation of how porosity and capillary structure determined concrete lifespan. In 1925, Dutch engineer Joosten patented a two-stage chemical grouting process. Pump sodium silicate into porous soil first, then pump a solution of calcium chloride. The two meet underground, forming a gel that locks sand and gravel into something approaching solid stone. The Joosten process stabilized soils beneath the Berlin Underground in the 1930s and remains a standard technique in soil stabilization handbooks today. By the 1940s, sodium silicate had quietly become the industry standard for densifying industrial concrete floors. Warehouse owners knew it, polished concrete contractors knew it, homeowners did not. When sodium silicate solution is sprayed onto cured concrete, capillary action pulls it into the pore network. Inside those pores, it meets free calcium hydroxide, left over from original hydration. The reaction is straightforward. Sodium silicate plus calcium hydroxide plus water yields calcium silicate hydrate plus sodium hydroxide. The same gel that gave the original concrete its strength forms again. Sodium silicate does not introduce foreign material. It feeds the reaction that never completed during the original cure. Newly formed CSH grows in the capillary once occupied by calcium hydroxide. The freeze-thaw pathway closes, the dust-shedding surface binds, and if the crack is narrow enough, it fills from the inside outward. Industry measurements report Mohs hardness, improvements of 30 to 50% over untreated slabs. A 2022 multi-scale study using a composite of nanosilica sol gel with lithium silicate and sodium silicate reported a Mohs hardness increase of 260%. That result belongs to the composite system, not plain sodium silicate. The honest figure for hardware store chemistry is 30 to 50%. Significant, durable, not magical. Chemistry does not need permission. If a grandfather poured a basement floor in 1958, the unhydrated cement is still there. It can still react. The crack he never quite fixed is, at the molecular level, still waiting for the silica that never arrived. Sodium silicate is sold openly by Foundation Armor, Concrete Sealers USA, Surfcoat, Ghost Shield, and a dozen other industrial chemistry suppliers, listed on Home Depot and in their own catalogs. The United States concrete restoration market reached roughly $4.25 billion in 2024 and is projected near $7.33 billion by 2034. Expert market research estimates the global concrete restoration market at about $17 billion. These are not small markets, and nothing is being hidden. The question is not whether sodium silicate is suppressed. It is why a homeowner walking into a hardware store at noon on Saturday will see 32 polyurethane crack fillers on the shelf and no water glass. 5 structural reasons account for this, none requiring a conspiracy. First, sodium silicate cannot be patented. The compound has been public since Fuchs documented it 200 years ago. No company can claim 20 years of exclusive sales. No exclusivity, no corporate champion, no marketing budget. Second, unit margins are low. Sodium silicate retails roughly $6 to $12 per quart. A name brand polyurethane crack filler tube sells for $20 to $30 and lasts 1 or 2 winters before failing. Shelf math favors the tube. Third, the product creates no recurring revenue. When water glass closes a crack by growing new CSH inside the capillary, the homeowner does not return. By design, the polyurethane tube does. From a business perspective, sodium silicate erases its own customer base. Fourth, there is no brandable SKU. Water glass is water glass. Homeowners cannot develop loyalty as they can to a colored, scented, branded sealant. No brand identity, no shelf priority, no advertising spend. Fifth, the channel is wrong. Sodium silicate is a B2B product. Sales calls go to industrial flooring contractors, polished concrete specialists, and warehouse facility managers. Homeowners are not the target. The chemistry never had a consumer marketing apparatus and never was going to. This is not a conspiracy. It is market drift, a solution that works permanently, cheaply, generically, and through a B2B channel cannot compete for shelf space against a solution that works temporarily, expensively, exclusively, and through a B2C channel. The only metric that matters in a basement is whether the crack closes. A product that works forever is not a product. It is a problem. The procedure industrial flooring contractors have used for decades, adapted to a basement crack, takes about 20 minutes of active work and a weekend to complete. Materials: 1 quart of sodium silicate solution at roughly 38 to 40% concentration, available from pottery supply houses, online chemistry suppliers, and most concrete sealer retailers. Typical price $6 to $12. A cheap pump garden sprayer costs around $15 at any hardware store. Distilled or filtered water for dilution. Optional for step 2, a small bag of calcium chloride, sold as ice melt, roughly $6 to $10. Preparation: sweep and vacuum the crack until no dust remains. If the slab is bone dry, mist lightly with plain water first. A thirsty slab will pull the silicate solution in faster than it can react with calcium hydroxide. First pass: dilute sodium silicate roughly 1 part to 4 parts water. Mist the crack and the surrounding 12 inches of slab until the concrete darkens but does not pool. Wait 15 minutes. Repeat misting until the surface stops absorbing, usually 2 to 3 passes. Wipe any white residue off the surrounding concrete with a damp cloth before it dries. Sodium silicate leaves cosmetic deposits if left on the visible slab. For cracks slightly wider than a hairline, wait 3 days for the first treatment to react and cure. Then mix 1 cup of calcium chloride into a gallon of clean water and mist the same area once. Wait 24 hours, then rinse with plain water. The two solutions meet inside the capillary network, forming an insoluble silicate gel, the same chemistry that stabilized soil beneath the Berlin Underground in 1933. The full materials cost is under $20. The chemistry is older than penicillin. 3 caveats matter, and any honest treatment must name them. Sodium silicate does not bridge cracks wider than roughly 1/16 of an inch on its own. Wider cracks must first be packed with fine silica sand, which the silicate then binds into the matrix. Cracks wider than 1/4 inch, actively growing cracks, or cracks caused by structural shifts or rebar corrosion under the slab, are not chemistry problems. They are foundation problems. The correct response is a structural engineer, not a quart bottle. Second, sodium silicate will not penetrate a slab already sealed with thick epoxy or polyurethane. The solution needs porous concrete to work. If the surface is glossy and beads water, the chemistry stays on top and dries to a film that peels off in a year. Professional epoxy crack injection systems, from Sika, Simpson Strong-Tie, and other specialists, bridge large structural cracks, cure in hours rather than days, and tolerate ongoing slab movement. Sodium silicate is the right solution for hairline cracks, dusting surfaces, weeping basement walls, and slow capillary failures that polymer fillers cannot permanently close. The right tool for the right wound. A wall in Privernum, Italy, has stood for 22 centuries because the Romans built repair into the recipe. A Ming Dynasty tomb has shrugged off a bulldozer because a chemist in 1500 added a bowl of cooked rice. Johann Nepomuk von Fuchs synthesized the first water glass in 1825, and the chemistry has been public ever since. Joosten patented the two-step process in 1925. Wigg at the Bureau of Standards measured how porosity affects a slab 110 years ago. None of this is hidden. It all sits in plain sight, outside the shelves where homeowners are taught to look. The fluorescent basement light still hums. The hairline crack remains, 3 feet long, a fraction wider than last winter. $8 of liquid will reach the unhydrated cement that has been waiting since 1958 for the silica that never arrived. Tonight, the bottle. Tomorrow, the mist. Find the smallest crack in the house. Measure it tonight against the edge of a coin, a quarter, a dime, whichever is closest. Photograph the coin against the crack with the date visible. Spray the solution as described. Come back in 30 days. The same coin, the same crack, the same camera angle. Post both photographs with the date and a single line of result. 6,000 basements in a comment thread can answer what the industry will not fund a study to compare. A 50-cent treatment versus a $25 tube. What was lost was not the chemistry. It was the habit of using it. The habit is 1 comment and 1 weekend away from returning. Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one.